Hello, my name is Jordan Boder.
I'm Isaac Yarbrough.
My name is Aaron Van Horn, and this is our water tower project. Who needs it and why? We chose to help a community in sub-Saharan Africa. In this region, access to drinking water is limited and often requires residents to travel long distances to collect contaminated water, which leads to preventable illnesses and daily hardship. To help with this issue, we designed a water tower to store filtered water close to the population center and be accessible by all residents with minimal physical effort.
In Deuteronomy 15:10, we are reminded to give generously without a grudging heart. And in Romans 12:10, we're called to honor one above ourselves. These verses guide our mindset while completing this project. They reminded us that we should remember the importance of serving one another. If we were to go through with the construction of this tower, it would provide accessible, clean hydration to those in need. It would allow us the opportunity to share the gospel with people who might not understand or even know who God is.
We were tasked with designing 2 different trussed water towers, both capable of supplying clean drinking water for a small population of 200 people. We are designing these towers for people of sub-Saharan Africa. Each person needs half a gallon of water per day, meaning the tower needs to hold 100 gallons of water. The trusses need to be capable of supporting the weight of the water and must be able to withstand the additional force of wind on the tower, which is 5 meters per second for average wind speed and 10 meters per second for double the wind speed. It must be made from readily available materials for ease of construction and repair. The forces in each truss member must be analyzed through simulation and hand calculations to ensure the truss meets our expectations and doesn't collapse.
So these are the designs. After many hours, we ended up with these 2 water towers. Design A on the left was our first design, and we were actually able to calculate the members in it, which inspired us to create Design B on the right. The tower on the left concentrated its distributed force more in the vertical direction than in the horizontal direction, which we found to be less stable than Design B. Design B provided a more even distribution. As can be seen at the corner of each tank, there are 4 members supporting their respective quadrants. Each member is at 60 degrees, which allows this tower to handle vertical and lateral loading extremely well, better than Design A.
Here are the technical drawings for both designs. Design A has a nearly cubic footprint, standing at just shy of 1.5 meters in all directions. Design B is 2 meters by 2 meters at its base, and also stands at just shy of 1.5 meters in height. Both designs can support tanks that are a maximum of 36 inches square at their base, but allow for taller tanks than the one we selected to be used. Here are the SolidWorks simulations for both of our designs. The pictures portray the designs at half their maximum capacity at 5 meters per second of wind. However, various combinations of half and full capacity, as well as the average and twice the average wind speed, were simulated for this project. Using these parameters, we were able to determine the magnitude of forces in the members of each truss. Our simulations proved to us that the designs meet our expectations and are even capable of supporting more than their expected loads. However, the simulations also made it clear that Design B distributed its load better than Design A, as Jordan mentioned earlier. This becomes apparent when looking at the colored force distributions of each model. Using the color scale at the right of each image, which portrays the range of forces on the tower, with minimal forces being blue, medium forces in green, and finally critical values in red, the far more even distribution of forces in Design B becomes obvious when comparing them to those of Design A.
To calculate the force in each member, we used the method of joints. First, we started by finding the reaction forces at the pins by summing the forces in the y direction and x direction and the moment about joint B. This gave us Bx, By, and Fa. These calculations can be seen on the left side of the work shown. Next, we started by drawing a free body diagram of joint B to solve for the forces in each member. After that, we did the same thing for joints A, C, E, and F. Those calculations are on the right side of the calculations shown. This is how we calculated the force distribution for each simulation for Design A. Design B had very similar calculations but included a roller instead of 2 pins. The only difference for those calculations was the reaction forces because a roller only has one reaction force in the y direction, which makes it a little easier to solve. Based on our simulations and hand calculations, design B was a better design. We made this decision because the forces were more evenly distributed in design B, meaning it is stronger and can hold more weight. It also uses less unique parts than design A, which will make building it easy. Not only can it hold more weight and be easier to build, but our hand calculations were closer to the actual forces in each member, causing a smaller percent error of 0.3241%. This is important because it shows that our hand calculations were fully correct and the truss is more predictable during different loadings. Finally, if the community we are providing for wants to add a larger tank, this tower would be able to hold it.
These are the materials that are necessary for building design A or design B. It is important to note that design B will be more expensive to build because it needs more materials, but the benefits of the tower outweigh the costs of the extra materials. All these materials are easily accessible at any Home Depot along with other various hardware stores, and this is important because it makes it easier for people in sub-Saharan Africa to get or make materials if a repair is necessary.
Here is the overall assembly procedure for our truss. Step 1, prepare the base. Dig shallow holes on a level surface, pour concrete footings, and set metal brackets for the vertical supports. Step 2, measure and cut wood. Measure and mark all lumber pieces, then cut them to size using a saw for accurate assembly. Step 3, build the bottom frame. Bolt vertical wood posts into the brackets and connect them at the base with horizontal beams to form a square. Step 4, add cross bracing. Attach diagonal braces between the vertical legs on all sides to reinforce the structure. Step 5 is to build the top platform. Secure horizontal beams across the top, then lay plywood to create a solid base for the tank. Step 6, install the water tank. Place the tank on the platform, center it, and fasten it with metal straps to prevent movement. Step 7 is the final check. Ensure all connections are tight, braces are secure, and the structure is level before filling the tank. And here's the slide for our references. Thank you.